Hi everybody, today we're going to talk about Newton's third law. But before we do that, let's recap Newton's first and second laws. All right, Newton's first law, it's called the law of inertia, basically boils down to this. A net force, or an unbalanced force, will cause an object to change its velocity. So first law, all right, unbalanced force, B-A-L-A-N-C-E-D, force, causes an object's velocity to change. Flip side of that, if the forces are balanced on an object, if the net force is zero on an object, no change in velocity. All right, and that change in velocity can be, which is not changing, I guess, doesn't change speed or doesn't change direction. If there's an unbalanced force, you're going to change the speed, the direction, or both. All right, that's the law of inertia. Newton's second law, the law. Now this one's an equation. This kind of puts a little math behind this one. That's pretty cool. The net force, which means the vector addition of all the forces on an object, is equal to the mass of the object times its acceleration. All right, so a net force will cause a mass to have an acceleration. This is a vector equation. The direction of the net force, the direction of the acceleration are always the same. What a wonderful equation. All right, third law. Third law is different from the first two. The first two talk about all the forces on one object. The unbalanced force on one object causes that one object's, remember it's apostrophe S, not S apostrophe, cause that object's velocity to change. Newton's second law, it's about one object. The net force on one object, all the vectors on one object added together, will cause that mass to have an acceleration. And the amount of the acceleration is proportional to the amount of force. And it has to do with the mass. The mass is the scalar there for that. Okay, third law has to do with two objects. Two objects. All right, here's the idea with Newton's third law. How can I explain this the best? If I push down on this piece of paper, the piece of paper pushes back up on me with the exact same amount. If I take my two fingers and I take this finger and I push this finger with 5 newtons. Here you go, I'm pushing with 5 newtons. What happens is this finger pushes back with 5 newtons. And it doesn't matter if they're moving at a constant velocity. It doesn't matter if they're accelerating while this is happening. If finger 1 is pushing on finger 2 with 5 newtons, finger 2 pushes back on finger 1 with the same 5 newtons. At rest, at a constant velocity, or accelerating all over the place. All right, here's Newton's third law. And I'm going to write the whole thing. It's going to take a while. For every force on an object, every single one, there is an equal and opposite force. I'm going to sneeze. I was able to hit the pause button before you had to live through that. That was ugly. All right. For every force on an object, there's an equal and opposite force on another, A-N-O-T-H-E-R, object, O-B-J-E-C-T. It's the idea here. For every force on an object, there's an equal and opposite force on another object. I push on you with 5 newtons, you push back on me with 5 newtons. I push on, I push on my computer monitor where I got the camera. I didn't know my finger was orange. The computer monitor pushes back with the same amount. All right. let me show you a couple things like this. This leads to something called Newton's third law pairs. At least that's what I like to call them. So how about this? I got a dude standing on the ground. All right, and I'm going to make the dude look like a box. Okay, so if the Earth pulls down on the guy with, I don't know, what's reasonable? 200-pound person with 980, so let's say 750 newtons. The Earth is going to push back up on him. We'll assume he's just sitting there. And this is going to be the normal force. We learned about that last time. And no motion. Velocity is 0. All right. So this is also going to be 750 newtons. That is not Newton's first law. What we're talking about there is an example of Newton's first or second law. That's not Newton's third law. I don't know if I said it wrong. That right here, this is not an example of Newton's third law. This is either Newton's first law, an object at rest will have all the forces balanced. Okay? Force up equals force down, objects at rest remains at rest. Or it's an example of Newton's second law. Hey, 750 up, 750 down, add those up, you get 0. 0 causes this mass to have no acceleration. Okay? That's Newton's second law. If I want to expand this to Newton's third law, here's what we have to do. We have to then break apart the objects, separate them, so I can now kind of see what's happening in between them. So here's the person, here's the ground. Now the person's still on the ground. I just have to draw them separately so I can see what's going on. We know the force on the person is, force gravity is 750 newtons, and our force up, force normal, is 750 newtons. Okay, but here we go. For every force on an object, every force on one of these, there's an equal and opposite force on another object. So let's take this normal force. The Earth is pushing up with 750. It just so happens that the box, and I'll call this force box, I'll put a B there. The box pushes down on the Earth with, you guessed it, 750 newtons. These are two forces which are third law pairs. Earth pushes up with 750 on the box. Box pushes down. Oh, no, I'm sorry. It's not a box. It's a person. Oh, no. I've made a person into a box. That's so scary. All right. Maybe the person's last name was Box. All right. Okay. Fred Box. Maybe. All right. So Earth pushes up on the person with 750. Person pushes down on the Earth with 750. That's Newton's third law. These are forces that are equal and opposite on different objects. Hey, you want to know what else? This person pulls up on the Earth with a force gravity of 750 newtons. Because if you recall, we didn't really go into it all that much, but any two objects out in space, is coming later in the class, they will apply a gravity force on each other. And you guessed it, it's the same number. All right, because of Newton's third law. Hey, this mass 1 pulls mass 2 with a certain force. Mass 2 pulls back on mass 1 with the same amount of force. Okay, this pulls up on the Earth, but the Earth doesn't move because it's so hugely massive. All right, so those are Newton's third law. At this point, I want to do one sample problem. And it's both going to tell you a little bit about Newton's third law, but also give you another practice at one of the solutions, ways to solve a problem in physics. All right, so we got frictionless plane. Frictionless. I'm becoming a good speller here. All right, I got a mass here. I will call this mass 1. And how big do I want to make mass 1? Let's make mass 1 8 kilograms. And over here, I should have made it larger. I got mass 2, and I'll make mass 2 2 kilograms. I'm doing this to make the numbers work out kind of nice. Now, I am going to push on mass 2 force push equal to 40 newtons. Okay? What I want to know is how big is the force of mass 2 on mass 1? How much is mass 1 being pushed by mass 2? So force of mass 2 on mass 1. Oakley dokley. So here we go, and I'll show you the tie-in. All right. The way you solve this is, well, the only way I can get to that force is I better figure out how much this object's accelerating. All right. And I'm going to do this maybe not in the most direct way, but I'm going to try and work in third laws here. All right. So here's the idea. Think of this as one object first and apply this force to it and find the acceleration of the one object. So our force push will cause mass 2 plus mass 1 to have some acceleration. The total mass to have acceleration. So our acceleration is the force push divided by mass 2 plus mass 1. So it's going to be 40 divided by 10, which is going to be 4 meters per second squared. It's almost like I picked those numbers out on purpose. All right, so now I know the acceleration of the whole thing. I'll use green for my acceleration. We got an acceleration of 4. Okay, if I want to know now how much mass 1 is pushing on mass 2, now that's really not the question here, but let's find out how much mass 1 is pushing on mass 2. All right, so now I'm going to look at just mass 2, just M2. And here's what I know. I've got 2 kilograms. I got the force push, and that's 40. I've got the force, I'll call this force 1, because it's from mass 1. And the question is, how much is that? And we also know, where'd the pen go? We know the acceleration here, acceleration is 4. All right, here we go. Newton's second law. Force push plus force 1 will cause mass 2 to have an acceleration. So that means force 1 equals, mass 2 acceleration minus force push. Right, that just comes over to the other side. So it's 2 times 4 minus 40. So that's going to be 32 newtons. Force 1 is 32 newtons. Mass 1 pushes on mass 2 in this setup with 32 newtons. All right, great. But what we really want to know is how much does mass 2 push on mass 1? So if I look at just, I'll change colors, just M1. Mass 1 looks like this. And it only has one force, and that's going to be force 2, and that's what we're looking for. Well, it's really easy. I know how much mass 1 pushes on mass 2. It's 32 newtons. Newton's third law. Guess what? If mass, 8 kilograms. If mass 1 pushes on mass 2 with a force of 32, mass 2 pushes back on mass 1 with a force of 32. So force 2 is 32. That's because of Newton's third law. Now, I admit, we could have just done all this and solved for that one directly, but I'm trying to work in Newton's third law, okay? And by the way, if you want to check this out, see if it all really, really works, watch this. A force of 32 applied to a mass of 8. All right, acceleration is force over mass. Force of 32, mass of 8. Guess what? We have an acceleration of 4. Just like we knew it was to begin with. We knew it was going to be 4. All right, so that's Newton's third law. All right, for every force on an object, there's an equal and opposite force on another object. I push on you with 10 newtons, you push back with 10 newtons, okay? Doesn't matter if constant velocity, zero velocity, or an acceleration. Objects always push back with the same amount, okay? And then I worked an example here to basically show you this idea of solve for the whole, apply the acceleration to 1 to figure out some of the forces. In there, I was able to work out Newton's third law, or put in Newton's third law, but admittedly, it was forced. Forced, get it? Forced. Okay, that's it for now. Adios. I'll see you around.